Let's take a look at these acid-base questions. Question 7.1 reads, sulfuric acid is a diprotic acid. 7.1.2, give a reason why sulfuric acid is referred to as a diprotic acid. So there is a definition that states that acids are proton donors when in solution. Now, what is a proton? When we're talking about acid bases, that section of acids and bases, a proton is referred to, or a proton is an H plus. Okay, so 7.1.2, if we have sulfuric acid, which is H2SO4, and it dissociates, it will dissociate once as H plus HSO4 minus 1. There's still a hydrogen on it, so it can dissociate again. So the HSO4 minus can dissociate again as H plus, and then plus SO4 2 minus. Now if we count, it has dissociated once, it has dissociated twice. So it is a diprotic because it will donate 2 protons. Okay, so donates 2 protons. Okay, 7.2. The hydrogen carbonate ion can act as both an acid and a base. It reacts with water according to the following balanced equation. Write down a word for the underlined phrase. So something that can act as both as an acid and a base is referred to as an ampholyte. So 7.2.1, it is an ampholyte. Okay, 7.2.2, copy the equation and indicate the conjugate acid-base pairs. So HCO3 minus plus H2O gives us H2CO3 plus OH minus. So what you need to do here is you need to look at what that compound has become, right? If it gained a proton, if it gained a hydrogen, then it's a base. If it lost a hydrogen, then it's an acid. For instance, if I focus on the H2O, the H2O became OH minus. So in other words, it lost a proton, or it donated a proton. And we know that acids donate protons, so the H2O in this case must be acting as an acid. That means the OH minus must be the base. Then, so we can call this acid 1, base, let's call that base 1, right? Then that means the HCO3 must be base 2 and the H2CO3 must be acid 2. Okay? Moving on. 7.3. So question 7.3, a lab assistant was asked to prepare 2,500 centimeters cubed solution of HCl with a concentration of 0.25 moles per dm cubed. The lab had a bottle of concentrated HCl which had the following written on the label. So 7.3.1, calculate the mass of HCl contained in 2,500 cm cubed of 0.25 moles per dm cubed solution. So there is a form of the concentration formula that has mass in it, and it's actually quicker to use that formula. So the formula is concentration is equal to mass divided by molar mass times volume. We want the mass, so we should have everything else. Do we have the concentration? Yes, we do. Concentration is 0.25. We don't know the mass, so leave it as M. The capital M is the molar mass. It is the molar mass of HCl. You get that from the periodic table. Hydrogen has a mass of 1. Chlorine has a mass of 35.5. So the molar mass is 36.5. Now, the volume V, they tell you the volume. 2,500 cm cubed. We can't use cm cubed. We must use dm cubed. So divide that cm cubed by 1,000. You're going to get 2,5. So 2, 5. Now we can solve for mass. You take everything across, you multiply, you get a mass of 22,82 grams. Okay, 7.3.2. 50 centimeters cubed of the 0.25 moles per dm cubed HCl solution. So let's make a note. We're talking about the acid here. The volume of the acid is 50 cm cubed. Let's actually convert that, because so 0.05 dm cubed. We know the concentration as well. The concentration is 0.25. Then the base, the volume of the base is 20 cm cubed. So 0.02. And they want to know, calculate the concentration of the base. So they want to know the concentration. Now this is a neutralization, right? And there is a formula that you can use for neutralization. And the formula is Na over Nb is equal to Ca Va over Cb Vb. Now, Na is the number yet in the front. So we get this from the coefficients. So Na is going to be 2, because the acid, the number in the front of the acid is 2. So 2 divided by the number that's in front of the base is 1. So 2 over 1 is equal to the concentration of the acid is 0.25. The volume of the acid is 0.05 divided by the volume of the base is 0.02. The concentration of the base is what we want. So now just solve for Cb. And you solve, you get a concentration of 0.31 moles per dm cubed. Okay? And the last question, 7.3.3. Name a suitable indicator. So the suitable indicator that we can use for this kind of titration is going to be methyl orange. Now, why are we going to use methyl orange? Because HCl is a strong acid and Na2CO3 is a weak base. So whenever you have a combination of a strong acid and a weak base, methyl orange is your go-to. Okay, that's it. Thanks so much for watching, and I'll see you in the next one. Bye-bye.